In this second video of our series about serial rings, we will be looking at one of the situations that occurs with serial rings, namely one that was proved by Robert Warfield, that asserts that every finitely presented module is a direct sum of uniserial modules, namely every such module is serial. See, this certain serial rings admit such nice decomposition for some of its modules, and this one is the particular focus of this video. Now, as you will have noticed, this video is kind of less animated than the other ones that I've posted here before, simply because this way we can expedite the pace of the video, so it can run faster and it won't take as long as some others did. This next lemma is instrumental. So you take a right serial ring and take an ideal I, and notice that this I is equal to R times I, which, when applied to this decomposition here, gives you a decomposition of the ideal itself, that way. So the factor R over I is isomorphic to the direct sum of these uniserial modules. Which shows what? Which shows that the factor ring as a right R module is serial. But then, since the right ideals of R over I and right R submodules of it coincide, it gives us the desired result. So this was the theorem that I was talking about, which is what we'll do within the next few slides. So finitely presented means basically, or equivalently, any finitely generated projective factored with respect to a finitely generated submodule. Okay? Now, this next definition features a property that is enjoyed by certain primitive idempotents, primitive local projectives over serial rings, and it's kind of it's actually very useful for our purposes. So take two modules M and N. M is said to be almost n-injective if any map F from a cyclic submodule A of n into M extends to a submodule B of n such that one of the two things happens. Either B is n, in which case F will have extended completely to a homomorphism between n and M, or B won't necessarily be equal to n, but G will be an isomorphism. Okay. I mean, the extension is an isomorphism. What does it mean? Let's let's paraphrase it a little more friendly. So this is equivalent to saying that every F like that either extends to n, or it is one-to-one, and its inverse extends completely in the opposite direction, from M into N. So when it does that, it's going to be a monomorphism. That's another requirement of the condition. Now, extensions of maps are the main thing about injectivity, and they can be paraphrased or translated to the language of lattices of submodules, which some of you might find easier to wield, which is the content of the next lemma. So you take M and N, again two modules, and the submodule A of N. and there's a map f from A into M. Now, the extendability of f to a map from N into M is equivalent to this direct sum having a submodule T containing what I call the graph of f, such that T direct sum is equal to x. Okay. Now, let's notice a few things here, just for informational purposes. So we have the x equal to n direct sum m. Here's just a lousy picture of the situation. Let's say A is this, and then I have A star lying somewhere, not necessarily inside n, but with trivial intersection with m. So the first thing to notice will be A star intersect m is trivial. And A star is isomorphic to A. And furthermore, the intersection of A star and A is equal to the kernel of f. So these are the basic properties that you might find useful while trying to understand this whole thing. Let's get to the proof. Okay, so suppose that f extends to a map G from N into M. Then just take T to be this module. Obviously, it's going to contain the graph of f, because G, when restricted to A, is equal to f. It coincides with f on A. And it's an easy thing to check that T intersects with M trivially, and its direct sum with M is equal to the direct sum of N and M. Okay, that takes care of the first part. Conversely, if we have such a T as was described on the previous page, like this, containing the graph A star, and having direct sum with M equal to x, then what we do, we take this map pi, which is a projection of projection with respect to this decomposition onto M. Okay, so what we do is just to observe that the restriction of this pi to the module n is the desired extension of f. Why? Well, for any a, you can write a as the sum of a minus f of a, which now is the t coordinate of the element a, and this f of a now becomes the m coordinate of a. So the projection will take it to simply to f of a. Okay? So, okay. Now, the next result, proposition 2, has a similar flavor and can be proved easily by our audience. But I'll just indicate a couple of things here, just to give you a direction of what to do, maybe. Okay, so take two modules M and N. Again, let X be their direct sum. The almost injectivity of M is equivalent to this condition. Any cyclic submodule B of this direct sum, with trivial intersection with M is contained in some T, which is a submodule of X, whose direct sum with M is equal to X, or whose direct sum with N is equal to X. Okay. So what is this supposed to give you? Well, okay, to help you with the proof, I mean, hoping this diagram will be helpful. If you have a T, okay, obviously this B will be just the graph of any cyclic submodule of A, so that you would be taking to apply the definition of almost injectivity to. So basically, this will be your B. So this will be your B. So B represents the graph of any cyclic and any homomorphism on a cyclic submodule of N into M. Now, so that's what it is. Next, okay, let's draw a better picture here. So we have a B. If B intersects with, okay, so the first situation when there's a T satisfying this equality, T direct sum M equals X, that basically gives you the situation when F will have extended to a map from N into M. So F extends, this will indicate that F extends to such a map. That's the first situation. The second situation is when both B and T will have zero intersection with N. So it will be like this. And furthermore, T direct sum N will be equal to M, X, I'm sorry. Now this is the situation when F is 1 to 1 and F inverse will have extended to a map from M into N. That's that situation. I hope that this helps you prove the whole thing. Okay. What are we going to do with it? Well, the theorem 3 says if R is serial with a complete set of orthogonal primitive idempotencies, say EI, this means the sum of EI is equal to 1, and EI times EJ for distinct indices is equal to 0 for any pair of distinct indices I and J. And EI squared is, of course, because they are idempotents, EI squared equals EI. Now, in the case of a serial ring, each EIR is almost EJR injective. Or simply put, the principal indecomposable modules, namely EIRs, are relatively almost injective. And we allow for the indices to be the same, like each EIR is almost self-injective too. Okay? Okay, we'll just use the definition of almost injectivity. So here we are going to test the almost EJR injectivity of EIR, simply by using the definition. So take a non-zero cyclic submodule of EJR and let F be a map from A into EIR. Now, A being cyclic inside a uniserial module is itself uniserial. So we have this. And in this situation, in the situation of this ring, it is the epimorphic image, or an epimorphic image of one of these principal indecomposables, say EKR, and assume the assume that rho is an epimorphism from that module onto A. So we have this sequence of maps, F and rho. Now, if you go back and look at the situation, both rho and the composition F rho can be viewed as maps emanating from EKR and ending inside R. So they're both members of this home group. Now, this is isomorphic to the left module. It's an R isomorphism, a module isomorphism, to the left module via this association. Well, in this case, what it means for us in particular is that if G is a map from, say, EKR into R, and R is an element of R, then the action of RG on any element X will be R times G of X. Let's keep that in mind. Okay? Now, and because of the seriality of this as a left R module, there's an R such that one of two things happens. One, either R times rho is equal to F rho. It should be F rho. Which is the case when rho R contains F rho R. Oops, made a mistake. Okay. In fact, this was inaccurate, of course. This should be the opposite way. Yeah. This is the case when this inclusion happens because of the uniseriality. And this is the case that depicts the reverse inclusion. Okay. Now it's correct. So in the first situation, when R rho is equal to F rho, we simply have that the left multiplication by R and the map F coincide on the image of rho, which happens to be A. So then we have a hope for an extension of F here to the whole EJR. But then you see we might not be able to take the extension of this map to EJR simply because its image may spill out of the EIR. So in order to tame that image, what we do, we simply compose it with pi I, which is the projection of any element with respect to this decomposition into principal indecomposables onto the EIR. If you do that, that way you will have made sure that the image of decomposition, which is this thing, will fall inside the EIR, and it will not affect, composing with pi I will not affect the left multiplication by R of elements inside A, because R dot already coincides with F on A, so its image as far as A is concerned is already inside EIR. So that gives us the first situation that was given in the definition of almost injectivity. In the second situation is naturally expected to give the other one, which is this: rho is equal to RF rho. Well, in this situation, the composition RF and the identity of A, identity map on A, coincide on A. So, in other words, the left multiplication by R acts like the inverse map to F when restricted to A. Then we act in a similar way as we did before, and we compose to make sure that the image of R dot will be tamed, in the sense that the ultimate image of this composition will end up inside EJR. So this time I used the projection onto EJR instead of EIR. Remember that projection would be this similar to this one. Instead of I, you take J, then you get your P, the pi J, the projection pi J. Yeah. So now then it's easy to see that this composition extends the inverse of F on the image of F to a map from EIR into EJR, and that will be a monomorphism. The reason being that these guys are uniserial, and once F is 1 to 1, namely so is F inverse on the image, and assuming that its image is non-zero, of course, F inverse, okay, the extension map, which is this thing, will have kernel intersecting, oh, sorry, I'm saying it wrong. Okay, this thing, the extension of the inverse, cannot have kernel non-trivial because we are inside a uniserial module, and it's easy to see that, really. So this yields the conclusion. Okay, so once again, what have we proved? We have seen that if R is serial, then the principal indecomposables are almost relatively almost injective, which we will use in the next one. So the next lemma 4, says that if P is a direct sum of finitely many uniserial modules that are relatively almost injective, then every cyclic uniserial submodule of A is contained in a uniserial direct summand of P. Okay, this will be instrumental in the proof of the main theorem, the one that's due to Robert Warfield. Okay, so first let's note this. Let's look at the statement inside the parentheses. It refers us to proposition 2. Go back to proposition 2 then. Oops, I went too far, I guess. Okay, here's the proposition 2. Here, if you take M and N to be uniserial and uniserial, then the proposition 2 says any cyclic submodule of B with trivial intersection with one of these things. Assume that M and N are both almost injective relative to each other. So in that situation, this proposition says that any cyclic submodule which has trivial intersection with one of these M and N, in which case that cyclic submodule would necessarily have to be uniserial because of embeddability in one of the M and N by the obvious projections. Then in this case, that B is contained in a direct summand T which either complements M or N. So let's go forward. Now, but we have N, possibly way more than 2 summands here, so that calls for induction, an obvious induction. Now take a cyclic submodule of P and let it be uniserial and cyclic. So let it be generated by an element such as A, and write A as as a sum of its pi coordinates, each one coming from the capital Pi. So we will immediately move on to the inductive step of the induction. So what you do, just assume without loss of generality that each of the pi's is non-zero, otherwise there would be nothing to prove. Now, p1 plus p2 is the image of A under this projection that I'm pointing at right now. And the so the submodule generated by p1 plus p2 is the epimorphic image of AR under this projection. Therefore, it is itself uniserial. And it's a uniserial submodule of p1 plus p2, to which the remark that you see here in parentheses applies. Right? And what happens here is that p1 plus p2r is contained in some uniserial direct sum and p prime of p1 plus p2, the direct sum p2. And since that p prime will be replacing one of p1 or and p2 in the direct sum, it's going to be isomorphic to one of them. Let's say it's isomorphic to p1. This way we make sure that p prime and the other pi's are also relatively almost injective. And the nice reduction here is that A is now contained in the direct sum of these n-1 modules, which satisfy the same hypotheses as we said at the beginning of the theorem. I mean, the same ones as pi's do. So now the conclusion follows by induction. Okay. Okay, now this is the key proposition that pretty much yields Warfield's theorem. So if R is serial and P is a finitely generated projected module over this ring, right or left doesn't really matter now, and if M is a finitely generated submodule of P, then you can find a decomposition such that M is the direct sum of its intersection with the pieces, those pieces in the direct sum of P, or the direct sum that will yield P. And this direct sum will consist of uniserial components, pi's. You see how this would yield the desired result due to Warfield. Then any finitely presented module is in the form P over M for such a P and M as are described here. So that P over M would be isomorphic to the direct sum of the Pi over Pi intersect M's, each of which will be uniserial. And then the result would follow. Now, the proof of this thing is too long for me to be crowding you with, or crowding your minds with my voice. So instead, what I'm going to do is I'll let the viewers peruse the proof, but in the meantime, I'm going to give you a summary. I'm going to walk you through the proof, not the whole proof, but a summary of the proof. I think that way it will be better understood. Okay, so all right. So you see, P is finitely generated. That means P has finite Golgi dimension. It's a direct sum of finitely many uniform. It's actually more than uniform. They are uniserial modules. And if it's a sum of n uniserials, then its Golgi dimension will be n. And M being a finitely generated submodule of P, it's a sum, not necessarily direct, of say m lowercase m uniserial modules ui. So the proof will do induction, but it will induct on the sum of these two quantities, namely n plus m. Okay. So at the first Step of the proof, you will isolate one of the UMs, one of the UIs, namely the last one, and call the remaining sum M prime. So that will give you M prime plus UM equal to M. The reason for doing this is because we have the previous lemma at our disposal, which enables you to enclose UM inside the uniserial direct sum of the direct sum P1 through Pns, which is, I guess, indicated here. Oh no, that's not that one. Let's see. Okay, it is this one. Let's go to the next page, the previous page. Now what happens is M prime is now inside the direct sum of n minus 1 projective uniserials, P2, P3 through Pn, to which you can apply the inductive hypothesis to get a decomposition no, I'm sorry, I said it wrong. What I meant was this. M prime, in the M prime we have a fewer number of uniserials adding up to M prime than M, right? So it is still contained inside P, not necessarily the last n minus 1, which means the inductive hypothesis first applies to P and M prime. So this decomposition along with M prime. Apply the inductive hypothesis to these two to get you a decomposition like this. So the PIs will give you that decomposition. Okay, so furthermore, you will have the UM enclosed in a direct summand D of P, a uniserial direct summand. And now, since D is a direct summand of a projective module, it is itself projective, and plus it's local. And we know that local projectives are in the form ER, and their endomorphism rings are isomorphic to ERE, the corner ring, which is local. And the local modules have what we call the exchange property, which means that D replaces one of the PI in the direct sum. So we have a situation like this. P can be written as a direct sum of uniserial projectives in two ways, like this or like this. Also remember that the sum of these little pieces here gives you M prime, and the sum of M prime and UM gives you M. So now we look at these projections, obvious projections, onto the respective modules P1 and D with respect to the direct sums that you see here and here. Okay, what about them? In the first case, so you see you project UM by pi 1 into P1. If this projection P1 of UM is contained in M prime intersect P1, then here's what you can do. See, the M, which is the sum of all these little pieces that you see here, all these things, is now a sum, the sum of this piece plus the projection of this guy into the last n minus 1 pi's, namely those from p2 through pn. That's given in the next picture. So that's basically what it says. If this is the case, then this sum is equal to this direct sum, and if you let n be the sum of p prime of um, namely the projection of um inside the sum from p2 through pn, and the rest of the m prime intersect pi's, then m direct sum the first m intersect p1, that's the m intersect the first p1, then that's equal to m. Now, by focusing on n, which now is contained by the direct sum of these n minus 1 modules, once again you're able to apply the inductive hypothesis, so that instead of the whole p, just this part of the direct sum has a decomposition that satisfies the assertion, namely something like this. So now we have pi primes in your decomposition, and n is just their intersection, the sum of its intersection with those pi primes. But then here's the thing. Now m is equal to n plus this first thing, m prime intersect p1, and you can easily notice that it is equal to this direct sum, which is what we wanted. So the decomposition, the complete decomposition of p into the desired modules would be would involve p1, p2 prime, p3 prime, and so on through pn prime. So that would be the desired decomposition. Now that takes care of case 1. Remember what case 1 was. In the case 1, the projection of this um into p1 was contained in m prime intersect p1. What if it wasn't contained in it? You see, we're working, in either case, we're working in a uniserial module. I mean, p1 and d are isomorphic to each other, they're uniserial. So it's either that, namely p1 um contained in m prime intersect p1, or the opposite inclusion, namely this. Well, in that case, then you would do the exact same thing as we have done in case 1, except you would be interchanging the roles of, let me clear this place a little bit first, the roles of p1 and d, and those of m intersect p1 and um. And instead of pi1, you would be focusing on pi2. You'd be using pi2. And you'd carry out the exact same argument, essentially. So that's the gist of the proof. I hope I didn't confuse you that much. But I think the proof, the way I wrote it here, is quite easily legible and hopefully not too hard to understand. Now, the corollary is the result of Warfield. Every finitely presented module over a serial ring is serial. And thank you for listening.